All right, folks, welcome back to Science 30. Today we're going to be talking about fields. There's going to be two videos that we see today. The first one's going to just be about fields in general, so no real math to that. And then the second one is going to be about the mathematics of fields. So we kind of have to start out by not necessarily giving a definition, but talking about what a field is. So there are some pretty complicated definitions. Please don't just jump into Google and be like, what is a field? Obviously, there's lots of different words or meanings for the word field. It could be a wide open grassy space. We're definitely not talking about those. It could be an area of study, like, so-and-so is one of the most distinguished scientists in the field of chemistry, or something like that. Could refer to a certain kind of area where you play a certain kind of sport, like the soccer field. But a field in physics is, and this is my own kind of definition, it's an invisible force that's spread over a volume. In other words, there is a source for that field, and that field can exert a force, which is a pull or a push. You've empirically experienced this if you've ever played around with magnets. For instance, if you have two bar magnets and you bring the north and the north pole, so not matched up, you bring them together in the way that they don't want to be, you experience a push. And as a matter of fact, we're going to be able to talk about the way that field lines are drawn, because showing how a field works depends on our ability to kind of draw what the field looks like. And amazingly enough, since they're invisible, we're kind of in trouble for that. But there's different ways that fields can be visualized. So yeah, if you take two magnets and the matching poles are together and you're trying your hardest to push those together to touch, if they're good magnets, they're gonna push away really hard, and you will notice that the closer you get those two ends to each other, the harder it is to get them closer. So as they get closer and closer, the force actually increases. But we'll talk about magnetic fields in a bit. There are other kinds of fields as well. There's two that we're going to be talking about in more depth, and that is the electrical field and the electrical field and the gravitational field. Those are the ones we're going to be doing actual math on in the other video. So let's start out with the very first. Actually, let's just do a magnetic field. I'll shrink this down so it's a little bit more manageable. So a magnetic field only affects certain things. Obviously, when you were in grade 2, you played around with magnets, probably. You might not remember it. But we know for sure that there are some objects that magnets can't affect. Even if you have a super strong magnet, a magnet isn't going to be able to move, for example, a piece of plastic. Unless there's like a certain kind of metal stuck on it or glued to it, then it'll move. But a piece of plastic alone is not magnetic. Wood is not magnetic. Glass is not magnetic. Just to name a few things that I see on my desk here, fabrics are not magnetic, unless they've been woven in with pieces of metal wire. So magnetic fields they only affect certain kinds of substances. And we call those substances magnetic substances. They also affect objects that have a charge. A good example of this would be things that have a plus or minus charge. So protons having a plus charge, electrons having a minus charge, ions having a plus or minus charge depending on what kind of chemical they are or what kind of ion they are. So the way a magnetic field works is the following. I'm going to draw a magnetic field. Let's get my marker. There we go. So I always like to just do a very simple bar magnet for this. And magnetic field lines for a magnet, like a bar magnet, well, actually any magnet, the magnetic field lines go from north to south. I'm actually not going to have enough space. Eventually these magnetic field lines we just kind of say, forget it, and we can draw them coming out of the north side of the magnet, the north pole of the magnet, if you will, and then coming into the south pole of the magnet. Not a too shabby drawing. I'll put an image up on Google Classroom as well. I think there's even one in the textbook. So magnetic fields only affect certain kinds of substances, and they also affect charged objects or particles like protons and electrons and neutrons. Something that we will see is in common for all fields. Fields get incredibly wimpy the farther you are away from them. So if you have a magnet and you have like a quarter beside it, the magnet will probably affect the quarter. But if you move that quarter a couple centimeters away, that might be too far for the magnet to really drag the quarter. So the magnet may still be exerting a force on the quarter, it just might not be exerting very much. And fields, like I said, they get super weak the farther away that you are from them. This is going to be a big deal because guess what? We have math about how much weaker they get depending on how much farther away they are. So we'll talk about that in the second video. The second kind of field that we care about is a gravitational field. Now, you may be under the impression, and it's fine, I don't blame you if you do, you may be under the impression that gravity is super strong as a force. But I'm going to tell you this right now, it's actually not. It's actually a very weak force. Now, I know you can't jump in the air really hard and go to space. And usually when people think about what's hard and what's strong and what's weak, they think about the capabilities of like their own body. Or like gravity. How do we get into space? We have to strap ourselves into a giant rocket that goes incredibly fast in order to get into space, in order to break out of Earth's gravitational field, or at least move farther away from the center of the Earth. Because even in orbit, we're still actually tethered to the Earth by this gravitational field. So the cool thing about gravitational fields, they affect everything with mass. So there are things that are not mass. We call that electromagnetic energy or electromagnetic waves, and gravity cannot touch or affect or move or exert a force on electromagnetic waves because they don't have mass. Light is an electromagnetic wave and it doesn't have mass. I know it's very, very strange to think about a thing that doesn't have mass, that you couldn't put on a scale and measure. Because, I mean, you think about an electron, we're not going to be putting it on a scale, but we can measure how heavy it is. And they're tiny. We could measure a proton and find out, well, how heavy it is. We could measure a little atom, like a little, I don't know, an oxygen atom, and find out how much it weighs, its mass. But light and other electromagnetic forms of energy, they are massless. That has more implications that we'll talk about in Chapter 2. But, long story short, gravitational fields only affect things that have mass, and they pull those objects together. So it's not like a magnetic field where we can have two norths facing each other and that creates a repulsion, a push-away force. Gravity doesn't have a repulsive push-away force. As far as we know. It might. We're babies as far as gravitational science. We're still trying to disprove some stuff that Einstein said about gravity. And when I say trying to disprove, that's how science works. We want to try to disprove as many things as we can. We're supposed to be a little bit crabby and argumentative because we're like, we want to really put theories and ideas to the test and really give them a workout. Like you guys. Yeah, I could just give everybody 100%. I'm not going to, though. I have to put you to the test a little bit. I have to see, what you know and how much work you could complete, and are you, coming along with the class. But yeah, for gravity, it's always an attractive force, meaning it's always a pull. And in general, and we'll see this later, gravity affects literally everything. So I've got my watch. I haven't put it on. It's on my desk. And I've also got, I don't know, I've got a pen here. Those things have mass. Does that mean that the pen is exerting an attractive force on my watch? Yeah, actually. Everything is exerting an attractive force on everything else. I've got my coffee cup and my cell phone here. Do they weigh a lot? Do they have a lot of mass? No. They're about 35 centimeters apart. They're not going to exert a whole lot of force, but they will exert a little bit. It's funny when we're in a traditional classroom and we do this, what we do sometimes is we figure out the amount of force, when we get into the math, that two students would exert on each other if they were sitting beside each other in a classroom. And it is measurable. It's not very big. It's not like 40 newtons or something like that. It's a very minuscule number. It's a tiny amount of force, but it is a force nonetheless. What we also have done sometimes is take a look at how much gravitational force planets exert on us. So you might think about, okay, how much force does the planet Jupiter pull on us with, versus how much force does the planet Neptune or Mars pull on us with? And yes, they are measurable. You'll get a number, but the amounts are very, 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 very minuscule. It's tiny. And so in order to draw or explain what a gravitational field looks like, I'm going to have a mass. I'm just going to call it mass 1. And I'm going to have a mass 2. And so I'm going to complete these lines here. Now every single object has those lines going to it, but I'm going to prioritize the mass that's heavier, or the one that I've drawn to be bigger. I'm not going to go all the way around the circle. Yes, I am. And one thing that is kind of common to all fields is this. And actually, I'm going to edit this a little bit. I'm going to actually erase, I'm going to move mass 2 kind of out of the area, and I'm going to give it its own gravitational field lines. But the kicker is I'm not going to give it as many. And I'll explain why in a moment. So, the big thing about fields the more densely packed the field lines are, the stronger the field. So here we've got mass 1, it's obviously big compared to mass 2, and there are a lot of field lines here. That would mean that this has a strong gravitational field. Here we've got mass 2, it's obviously smaller, and since it's smaller, it's got less mass, and that means that the field is comparatively weaker. So yes, when you jump in the air, you are actually pulling the Earth with you. Is it a pull that's very strong? Is it going to move the Earth? No. The Earth is so massive. I think it's 6 point something times 10 to the 25 kilograms. It's an enormous number that we're going to have to do math with later on. But, you know, big numbers, small numbers shouldn't freak you out. They're all just numbers. They all have to obey the same rules. So let's talk about the electrical field. An electrical field only affects objects that have a charge. And we'll talk about this more in depth, but charged objects could be big, like a thundercloud. They could be medium size, like a balloon that you rubbed on your hair. Or they could be microscopic, like protons and electrons and ions. They could be electrons inside of, I don't know, a copper wire. In the next part of the chapter, we're going to be talking about electricity and how to generate it. And the cool thing about that is, yeah, it involves a very, very close relationship between electricity and magnetism. And those two forces are so tight that a scientist named Michael Faraday, who is a super genius guy, managed to stick them together. And instead of just being electrical field and magnetic field, he actually got into the idea of those are two sides of the same coin, electromagnetism. But anywho, the way that a charged, electrical charged field works is we have lines, and these field lines are going to be going in a particular direction. So I'm going to draw that for you now. Now, one thing that we kind of need to understand about electrical field lines. There are two kinds of electrical field. You can have a positive electrical field, or you can have a negative electrical field. What we do in order to imagine what's happening is we use something called a test charge or a test point. And in an electrical field, that point has a positive charge. So I'm going to draw what a positive charge would do to a positively charged test point. And the lines for a positive electrical field radiate outwards. Why is that? Because if we had a little test charge here, it would be, it would be pushing away. Sorry, I'm drawing badly here. Let's try that again. Go to positive test charge, and it's going to have positive field lines coming out of it. And so a positive test charge will interact with a positive electrical field by repelling, by pushing away. Opposite's going to happen when we have a negative electrical field. The field lines for a negative electrical field are towards the negative electrical field, towards the source. So if we were a positive test charge in this case, we would be, if we're positive, we would be attracted towards the negative field. This is why when you rub your hair with a balloon, your hair actually acquires a temporary positive charge, and the balloon acquires a negative charge. The reason being the balloon is stealing electrons from your hair. You might think, well, how come electrons are moving? Like, why do they even get to move? It turns out that they would just rather be around that rubber of the balloon. That's a more kind of, I don't know, hospitable environment. It's a place that the electrons would rather be. And so when you rub a balloon on your hair, electrons go from your hair to the balloon. They cause the balloon to become negative, and then in comparison, your body is a little bit positive. And if you just let go of the balloon, it'll just stick on your hair because of electrostatic attraction. So those are the three types of field. We have electrical, magnetic, and gravitational. We talked about the test point as well. The next video is going to be a little bit of information about electricity and voltage. And then the video following that is going to be about the electrical field and the magnetic field. And there's going to be examples for those. So see you soon.